Hello, how are you all doing today? Today we are going to be learning, as I share my screen, we're actually going to be learning addition reactions together. And um, because this is my first live, right? Kind of hearing myself. So I'm learning how to set this up. And I hear myself. So I think I have to figure out how to not hear myself. Okay, perfect. I think I figured that out. All right, so let's get started. I'm going to share my screen here, and we're going to be working on problems of the addition reactions. All right. Um, so if you are here, say hi and feel free to also um, yeah, it's fun, right? When you're doing things for the first time, it's so exciting. And at the same time, it's so confusing and so new. Okay. Um, so my computer is acting up right now, obviously, because it senses something foreign, right? And foreign is a problem. Okay. So let's see if I can actually figure it out. Yeah. Okay. We are back here. Um, and I wonder if my computer is like just not able to take the load of. Okay, let me stop sharing my screen. Okay. I think I would need like a second to figure this out. Um, the first times, like the things that you do the first time, they just excite me so much. Um, because if you keep doing them, of course you like get better at doing things. But the first time when I actually went for a walk by myself, like alone, and like not having to need anybody like in my life and just doing things by myself was that was nerve-wracking, right? And exciting at the same time. And then of course, like I became stronger and I never needed anybody, and then I could do things by myself, which was cool and fun. Of course, my uh I grew in strength over time, but it was not as exciting as when I did it for the first time and I wasn't sure if I'll be able to do it or not. So, okay, I'm trying to share my screen again and let's see if it's gonna work. But I'm also trying to close my tabs because um technology problems or technology needs to be used properly. Okay. All right. So today, or before we get started, I would actually like to introduce myself. If you guys don't know me, I am an organic chemistry tutor. Okay. And I have a PhD in organic chemistry. And I have been tutoring, I have TA'd for organic chemistry or TA'd chemistry classes for the last 5 years when I was in my PhD. And then for the last 2 years, actually, I've been tutoring organic chemistry and general chemistry courses. Um, and so I decided that why not start to teach online as well. Okay, so we are ready. And first of all, I just want to make sure if I'm even live. That's the fun, exciting thing about doing it first time. Like things are all over the place. Okay, where am I? Uh, am I still streaming? Yeah, I am. All right. How do I? find myself on the stream. Like, where am I streaming? Maybe I could double check on my phone, right? That's such a good idea. Okay. Well, the 4.0 Orgo Club is live. Yes, clearly it is live. Perfect, right? Nice. Okay, so let's get started now. I'm going to now share my screen here and let's see. Okay. All right, perfect. So now for the addition reactions, we are going to first look at a mechanistic problem where we are going over the mechanism of each of the following reactions. I've created a worksheet which covers like most of the chapter of alkene. So my goal is to cover most of these reactions, like cover most of the chapter in 20 minutes, right? Let's see if that's even possible. That's my goal. I'm not sure if that's possible, but let's try, okay? So in these next 20 minutes, I'm going to go over everything that is like the most important for an addition reaction of an alkene, okay? All right. Maybe I can get my head in there. Okay. So the first reaction is when you have a alkene, right? And we are proposing a mechanism for reaction with H plus and water, right? H3O plus is nothing but an H plus and water. So in the first step, if you actually have an alkene, we would first form a bond with the H plus. And what that does, right, is the alkene can actually be thought of as a nucleophile, right? And now a H plus is actually more of an electrophile, right? So in the first step, a nucleophile attacks the electrophile. And when that actually happens, think about the two electrons of the double bond, which are more like the electrons, right? That are more movable electrons. So those two electrons of that double bond will pick the hydrogen. Okay, so these will actually pick the hydrogen. And so when that actually happens, we will see that the carbon, which is less substituted, the carbon of the double bond, which is less substituted. So for example, these are the two carbons of the double bond. And if you actually think about, I'm just going to number them 1 and 2. The first carbon of the double bond is less substituted, right? Now, the second carbon of this double bond is actually more substituted. So the carbon, which actually is less substituted, forms a bond with the H. So carbon 1 forms a bond with the H. And then what would happen, or what happens then, is trying to play around with my screen really fast. Okay, so then what would happen is that we actually form a carbocation at the second carbon, right? So now if you're forming a carbocation at the second carbon, and the Markovnikov rule actually says that, right, a carbon at the more stable position would be formed. So a carbon which is more substituted, a carbocation which is more substituted would be formed, okay? And then in the next step, the water will just attack, okay? So now this water can be thought of as a nucleophile, and that nucleophile will form a, this nucleophile will actually attack at the positive carbon of that carbocation, right? So again, this again can be thought of as a reaction of a nucleophile and an electrophile. And always remember, the arrow has to go from the lone pair of electrons to the positive charge. So now the product of this reaction will look like OH2 forming a bond here, right? And of course, the next step is going to be to make the final product neutral. For that to happen, we'll use the extra water used in the reaction to grab that extra hydrogen, put the electrons back on that oxygen to make the final product a neutral final product. So this is the product of the reaction, and this is the mechanism. And now if we actually think about the second mechanism, I'm not going to go over, right, all of these problems, but I want to go over the second one, because if we actually think about the second reaction, what we do see is that the OH is not actually getting added on this double bond. The OH is actually not getting added any of the carbons of the double bond. It's just getting added somewhere else, which is on this carbon, more like a tertiary carbon. So we can clearly see here that a rearrangement is actually happening, right? So the carbocation is formed at a different position than on the double bond. So for those type of mechanisms, you have to think about the possible rearrangements that can happen because of carbocation rearrangements. So you have to know the carbocation rearrangement. So I'm going to use only 2 minutes to actually explain this mechanism, okay? And then we have H plus acidified water, right? So then in the first step of the reaction, we would actually use the double bond to form a bond with the H plus. And when that actually happens, we would form again a bond with the H and a carbocation. But now at the carbocation, if you see a neighboring carbon, which actually more has like a more like a tertiary carbon, right? We have a tertiary carbon as the neighbor. Now this hydrogen of that tertiary carbon can actually move over to the carbocation to form a new carbocation, right? When that happens, we'll form a better or a more stable 3-degree carbocation. And now when the water will attack, I'm not going to explain the entire mechanism. When the water will now attack, it will just form a bond with the OH here. And that's how we got an OH at the new position of that alkene. All right, so this is more like the more important mechanism of an alkene reaction. Now, actually, let's just simply look at some of the important reactions of alkenes, okay? So for example, if we have this starting alkene over here, and or on this starting alkene, if I'm forming a bond, or if I'm reacting with mercury and then demercurating it using sodium borohydride, how the reaction works is, right, when we have mercuration, demercuration reaction, how this reaction works is that we actually add water, or we actually add H and OH using the Markovnikov rule, right? And the Markovnikov rule says that the more substituted carbon, sometimes they call it more crowded carbon of the double bond, forms a bond with the OH, or like the negatively charged species or the anion of this of your nucleophile, or actually the nucleophile of the reagent, right? So if we have acidified water, then OH can be thought of as nucleophile. I mean, water itself is a nucleophile. Of course, in the last step, when we make it neutral, we only end up with the OH. So the OH would end up here, and the H ends up on the first carbon. And this rule is actually called rich becoming richer, right? Because the carbon, which actually is more substituted, forms a bond with the negatively charged species of the reagent, right? And if we had HCl, then it would have been a bond to the Cl, because Cl is the negatively charged species, or the negatively charged anion of the reagent, right? So this is the product Markovnikov addition. One thing to remember always is whenever we're doing mercuration, demercuration reactions, we avoid rearrangements. We do not actually add any form rearranged products, which is amazing because you don't actually have to do a lot of work then to find your products. Okay, now the second is reaction with Br2 and water. So again, if you think about Br2 and water, all you have to remember, the first thing is that Br positive is like the electrophile in the reaction, And water is like the nucleophile in the reaction. So OH really from water is the nucleophile. And the second thing that you have to remember is that this reaction is more like a trans addition to the double bond, right? So if we form a bond at the more substituted carbon, again, rich will become richer. So OH will end up at the more substituted carbon. The Br will end up at the less substituted carbon. And right, the other thing that you have to also remember is that this will be a trans addition. An explanation of why is not within this 20-minute time period, okay? But we can definitely talk about it. And you can just let me know in the comments if that's something that you are interested in, okay? Okay, all right, the next one is, let's look at the hydrogenation reaction. If you have hydrogenation, pretty much like Br2 and water, or Br plus and water, will very quickly form bonds with the hydrogen. So if one of the hydrogen is pointing up, the other hydrogen is also pointing up. And that is just the reaction. HCl, again, it is very quickly, right? H positive, Cl negative, Markovnikov addition of HCl. So then again, rich becomes richer. The more substituted carbon will form a bond with the Cl, and the other one will form a bond with the H. Of course, I'm not considering stereochemistry in any of these reactions, except the fact that I said here will form a trans product. So we can also say an enantiomer will also be formed, correct? Okay, the next one. In the next one, I have KMNO4 NaOH cold, right? So in the next reaction, the product always is, we have hydroxide addition, which means that in the KMNO4, when it's basic and under cold conditions, we only do dihydroxylation of that alkene. What that means is that we are forming or adding the hydroxy groups. And again, you have to keep in mind that that will also be a cis addition of the double bond. All right. Cool. 5 more minutes. And the other important reactions, we have talked about Markovnikov addition. We have talked about addition of halohydrin. We'll talk about halogenations, hydrogenation. We have talked about. We'll talk about anti-Markovnikov addition, formation of epoxides, and those are like the most important reactions. Of course, there's this other one, which is ozonolysis. And yep, that's it. So maybe we can go over like one, you know what, I'm just going to add another arrow here and do an ozonolysis reaction. Okay. All right. So the first step, the first reaction is hydroboration oxidation. So whenever there is a hydroboration oxidation reactions, in that one, we always form an anti-Markovnikov product. So whenever you see H2O2, right, that will change your mechanism from Markovnikov to anti-Markovnikov. So whenever you have like a peroxide in the reaction, not necessarily hydrogen peroxide, but more like a peroxide, that will give you an anti-Markovnikov addition. Okay, so now anti-Markovnikov doesn't mean a rich gets richer. It means poor person is getting richer. The less substituted carbon of the two will get to form a bond with the negatively charged species, or the species which has more electrons. So I'm going to form a bond here with the OH. Okay, and the other one over here is a bond to the H. And that is the product of this reaction. And of course, this, what we have to remember is also that this is a cis addition. Of course, when you learn the mechanisms, it is helpful. It's easier to understand why it's cis addition and why it's a trans additions. Okay, and then the next is reaction with Br2. And if we think about the reaction with Br2, what that forms is that we carry out a trans addition of the BRs on our alkene. The next is addition of hydrogen or hydrogenation reaction, right? In the hydrogenation reaction, it's pretty simple. We add 2 hydrogen molecules, and that also is a cis addition to the double bond. Okay. Now, in the next reaction, we have HBr. It's called hydrohalogenation, right? Again, this is a Markovnikov addition of the HBr. What that means is rich becoming richer, right? The more substituted carbon, which is the one on the left of the alkene, will actually be bonded to the Br, which is the negatively charged species of the reagent, right? If you have HBr, you can kind of think of that as like H plus and Br minus, or delta positive on the H and delta negative on the Br, right? Okay, and then the next is that we actually form a bond with like the Br. Oh, okay, so with the H then, right? Of course, we are left with the hydrogen. So that is the product of this reaction. Okay, and then the next step is reaction with peroxide. Sorry, not a peroxide, but more like an MCPBA type of reagent. So whenever you have something like an O3 reagent, right, that is more like an MCPBA type of reagent, metachloroperbenzoic acid type of reagents, they always form epoxides on your benzene. So not on the benzene, but on the alkene. So the product will actually look like this. So we have a epoxide. Okay, and that is the product of the reaction. Now, the next is let's think about ozonolysis. And if we actually have a reaction with the ozone, let's think about how the product will form. So we'll break that double bond, and each carbon of the double bond, so the double bond, like it's completely broken. Each carbon of the double bond forms a double bond O, and that is the product of an ozonolysis reaction, right? And the other carbon of that double bond will also get a C double bond O. And of course, because every carbon can actually form 4 bonds, right? So 1, 2, 3. So the 4th bond is over here, which is a bond to the hydrogen. So this covers like 80% of the material for alkenes, like the reactions of alkenes. There are some more reactions that I've not covered here, but you should feel good that we have covered like a ton of material in about 20 minutes. And if you have any questions, feel free to reach out to me or drop a comment on this live. Or if you want, of course, you can reach out to me if you want personal lessons. I'm still tutoring for organic chemistry. I will leave my calendar link on my bio on my YouTube channel. And if you're interested, feel free to reach out to me. And good luck on the coming finals or whatever test is coming up for you guys. And hopefully I will see you guys soon in the next live.